Hi, I'm Nolan. I'm going to go through the week 1 script file for my class, Principles of Computational Biology. This is going to be an introduction to R. It is going to be fairly quickly. It also is intended for you to be following along and doing it. I don't know, put it on the TV, pull up YouTube, do all that fun stuff, work on it on your own. This is all about getting your hands to practice this sort of thing. Pause it every now and then, experiment with it, try to break it, see what the error message is, then fix it again. That's the best way to learn. This is something that just really benefits from learning by doing. So lean into that. All right, we're just going to get started. Right now I have the EduPod open. This is our RStudio server. This is hosted at UT Austin. I do often recommend that you install it locally. However, that process looks slightly different, and I'll call out some points in here, but I'm going to primarily show the EduPod because that's the one that, all else fails, you all have access in my class to the EduPod, and you should be able to get that to work. Your local systems can be kind of problematic to use just because they're all different. That doesn't mean you shouldn't use them. It just means it's a little bit harder, and it causes its own little issues. But frankly, those are real. But let's get started. So to start off with, I've deleted everything except for a few files I can't really easily delete. And so it should look pretty similar to yours as you reset things. You may have some old stuff saved from previous classes, but for the most part, we should be able to just get started cleanly. Now, right now I am in my home directory, and I know that because I can click on the word home, and that's what it says. My working directory is a little bit small on the screen, but this has a tilde symbol, which looks like this right here. Followed by that symbol, a / that actually stands for home, and then the / stands for directory, so home directory. Thus, my working directory is currently what I'm visualizing in my files pane. Now, if I wanted to, I wasn't confident in that. Okay, I could say go to working directory, and since my working directory is my home, it just takes me here. Now, let's try a few things. I want to make some subdirectories. One of the things I'm going to try to encourage in all of you, something that I have to fight with my own brain, is to stay organized. And it just really helps in the long term. It's good for you to practice. So let's do that. We're going to make a folder or / directory. Just treat those synonymously. For the class, which we're currently in, which is INB321G, we're going to make that all lowercase and all one word. If you don't do that, all of this is capitalization sensitive. There will be problems in the future. Now, if you did mess up, it's easy enough to rename. You just select this little, what's called a radio button, and then you click rename and you name it whatever you want. You'd hit OK and it'd rename it. No problem. Now, at this point, I'm going to actually make a subdirectory because we're going to have a different file for every week. Folder, sorry. Inside my INB321G, I'm going to make a Wk01, and again, that's all lowercase, so week 1. I do 01 because eventually we're going to get above 10, and if I didn't do 01, 11 would get sorted before week 2, and I wouldn't want that, so I do 01 and 02 and 03, and that way they always get sorted by name in the right order. Really just handy trick. Going inside of week 01, I'm now ready to try and get my file into this. Now, here is the step where it really changes between different operating systems. On the EduPod, we have our handy upload button. Very easy to use. You just click on the button. Oh my gosh, this is so tiny. And there you go. You just select the file. Now, you might not be able to see that. I just navigated through my file system to get to the right file. Then I select it. And it's uploaded. I can check it by clicking on its name. This is going to cause R to open the file, not make an object. A lot of confusion there in the future, but it's going to open the file and visualize it, and there it is. Now, the problem is if you're working on a local system, you don't have that upload button. And so what you'll need to do is you'll need to figure out where your directories are. There's a lot of ways to do that. The easiest one, though, is because the challenge is typically where is the home directory. If you've already made INB321G and you've already made week 01, well, they're in your home directory. So the crux becomes where is that? I did include a handy piece of code, so you can see it right here. You can just type that into the console, or you could just, I don't know, somehow open it up. But if you ran this in R, this is going to actually describe more fully what tilde stands for, because it's a location, an address is what we call it, or a path, synonymous again, on your computer's file system that describes the location of your home directory. So as I run path.expand, it's printing out where in my directory system that home directory is. And if I navigated to that location via like my normal browser, then I would be able to find it. So this is the EduPod, so that doesn't really help me because, well, I can just go through here and I can upload. But on your own system, you would then go through your File Explorer, find whatever location printed off there, and that should be where your INB is. And then you just copy and paste into the appropriate place. So give that some practice and some time. I promise you it pays off. This is truly something that is one of those just like weirdly hard steps that even very experienced people still get tripped up by. And frankly, it changes all the time. And that's part of the problem is there is no one size fits all. Different operating systems, different computer makers even get all of this stuff set up differently. And it just kind of is a bit chaotic. Okay. In the end, you should be able to test, ideally, if this is working I first suggest closing this file, because there is a chance that you had multiple files open and you'll end up editing not the one in Wk01 directory. It's a subtle problem, but it actually causes a lot of problems downstream. So close it down, go make sure you're opening up the right version of the file, and then click its name in the Files pane in order to open it. Once you've done that, you know that you're actually editing the right file. In fact, I could even just like make a small change, save it, and I can see that that change date, the last time it was modified, has been updated. So I'm super, super confident now I'm looking at the right file, not a copy that I accidentally copied over. I can now try to run this second line of code, and it ran without error. That's perfect. In fact, we can even see the very subtle change it made where this used to just say tilde. It now says INB321G /Week01 / indicating my working directory is now in the right place. And finally, when I say list the files in that directory, it's listing the names of the files in that directory, which is the file I'm currently in. And that's all set up correctly now. All right. Welcome to having set everything up. This is actually what we did in class, so let me just start moving forward. So the beginning of this is talking about the script files and our ability to do comments. So commenting, very important, allows you to say really whatever you want to. It starts off with the number symbol or hashtag or whatever you want to call it. And everything afterwards is a comment, and it's not interpreted by R. It's not like treated as a piece of code. I really suggest you lean into this, especially early on in your career, because you simply can't read it as fluently as you will in the future. And frankly, I have never looked back at a piece of code and just been like, man, I'm sure sad I spent so much time on these comments. I'm always thankful I put in more comments. Or at best, actually. Most of the time I'm like, oh God, why didn't I comment that? I have no idea what I was thinking here. Oftentimes I really want comments to be more focused on like the why of things as well, especially as you become more like fluent in this language. The actual what is happening is often not the problem. It's the why of what's happening. That's where you lose it. Like the strategy you had in your head, like where was I going from A to B on this particular step? When there's, 60 steps, it can get kind of tricky to remember. Okay, so I have a comment to myself and you, actually, so you should go read the AI policy if you haven't. But I had a comment to myself to remind me to talk about the AI policy. Okay, here's the deal. AI is not going away, at least not paid versions. I don't know about the free versions. I think some of that's probably going to be diminishing in the future, but these AIs can be really useful for troubleshooting and even brainstorming ideas, especially simple ideas, the kind of things that we cover in an introductory class, which makes them very tempting because they they a little bit hamstring you. They're not as good at more complicated things. They're not. They're very bad actually at understanding context of what you're asking, and of course they hallucinate solutions all the time. Now all of this is of course a moving target. They're improving all the time, but in the end, like the goal with this type of learning, like what we're doing of practicing and just trying to be able to problem solve in useful ways for the future, not necessarily just for R or just for this class, but trying to train ourselves to think in the right way to code in the future. Well, AIs are going to be part of that. And so like it's in your best interest for me to at least allow their usage. That said, I really have to encourage you to minimize that usage. Really lean into it only when you need to, because the vast majority of the types of things we're doing in this class are fairly simple. It's more about you thinking in the right way versus you just knowing the answer. And the problem is a lot of the AIs are just going to tell you the answer. It's not really in your best interest to have that happen. And so what I recommend is anytime you are using AIs, do not just ask it to tell you what to do. Ask it for explanations. Ask it for advice. Like, how do I pull information out of a data frame in R? And then when it inevitably tells you to use some sort of package that you're not allowed to use, because I only let you use base R at the beginning, you have to be a little bit more specific. How do I pull data out of a data frame in R using the $ operator, a thing we'll learn about in your homework next week, as well as in some in the future. As you get examples, you then take those examples that it tells you and apply them to this current problem. Now, here is like my like cutoff point. You may never, note, look, where's my camera? Hi. You may never copy and paste into or out of the AI engine. I don't just do this for my protection. I do it for yours as well. There is a lot of problems that can cause, problems that are incredibly difficult to troubleshoot, and you'll just get stuck. The other thing is AIs are, they're not intelligent creatures. They don't ask you for a lot of clarification. At least right now, they're not asking for clarification where something is ambiguous. Instead, they just guess. And that guessing is sometimes crazy, and it leads y'all down just wild paths that no human would ever go down. It's often very obvious because literally no human is going to sit there and guess every name of a column when you, the human working with the data, could have just opened up the data and looked at the name of the column. That's just not a process any human would come up with. It's only a process an AI would come up with. It becomes very obvious that you have completely bypassed our AI usage policy and you're putting in code you do not understand. Because that brings us to our second point in that policy, and that is if you are ever using code you don't understand, in order to incentivize y'all to experiment and to do the research needed to complete these problem sets, because again, you're not expected to know the answer, you have to go do research. You have to try new things that you might not understand at the time, but then you come to understand through experimentation and research. In order to incentivize that, I do allow you to submit code you don't understand, but with a caveat. You have to put a comment in there describing where you got this code from, what part you don't understand. And the worst that's going to happen is we just reach out and say, hey, I need you to go fix this code, but we're not going to take off any points as long as you go through and make these changes. Okay? That's the deal. I think it's fair. But in the end, we just want you to learn. And so, yeah. So in summary, never, ever copy and paste into or out of the AI. Don't put my words into it. Only type in your own words. Don't copy paste words out of it. Same for your friends and colleagues. Do not just copy and paste their code. Again, have them explain things to you. Have them help you understand it, but then type it yourself. If you do that, we're square. All right. I'm going to look back down at my screen now. This is getting too intense for me. All right. Back to table contents. All right, table of contents, very handy. You click right here, it pops up. You can go woo and go to whatever section you want to. The way that I do this is I have little pairs of comment symbols before and after, and as you add those in, they just get automatically added to the table of contents. Handy feature. I use it all the time. It's in most of the script files in this class, so you should take advantage of that. Let me make the screen a little bit smaller. There we go. Okay. So the question is, how am I adding sublevels to the table of contents? Well, you could experiment with it, and you could also just look around. So like here is one with 5 comments, 5 comments, 4 comments. So with 4 comments, it's 1 over. With 5 comments, it's 2 over. With 6 comments, well, I thought it would go 1 over, but you can get sublevels in some of these different ways. Let's see if I do this. Yeah, there we go. Once I've had a third level, if I add another comment, it creates yet another level. There you go. Okay, so that's how that works. You can also collapse them by clicking on these little triangles. Don't normally recommend it. I think that tends to get a little confusing. I kind of wish you could just turn off that behavior. But that's the answer. And also this method of me just kind of putting answers to the right of the word question or answer in the comments, and then you can visualize it by simply adding in a line break. That's common throughout my script files, so feel free to use that as needed. So what makes this a script file? Not much, actually. It's mostly just this .r at the end of the file. This tells RStudio that what I am currently opening is a script file. And I can show you what I mean here by simply changing the name of the file. So let me close it down first. I'm going to rename this. I believe that's the rename icon. I'm just going to rename it to txt, so text. When I do that, note it no longer is all nice and colorful. Additionally, this little button down here now says text file, and that's because it's interpreting it as simple text. And that's actually all an R script file is. In fact, a lot of script files for different programming languages, in fact, really all of the programming languages I can think of in actuality are just text files. Let's try make it a Python script file. So with a Python, I start to get the code colored right. But now if I try to run it, it's going to say, well, it's going to do a bunch of stuff. I probably shouldn't have done this. It's going to eventually complain that it can't interpret that code because, well, I haven't written in the right language. It's not written in Python. I'm going to pause my video because I think I just broke things. Don't do what I just did. It's going to cause problems. So be right back. And after crashing R, we're now back. And that's why you pay attention to the file extension, a very demonstrative example from me. So I'm going to change that back to .r. Oh, that's actually kind of cool. I think that's a modern change to RStudio. It actually automatically updated this to an R script once I changed that extension. Neat. Okay. But yeah, that's what a script file is. It is actually just text stored on the computer. So what does that mean though? What does it mean to be a text file, a plain text file? Plain referring to the fact that there isn't a bunch of markup. So I'm not saying things like bold. Stop being bold. This is similar to, but legally distinct from HTML markup that I just typed. But it's just plain text. There's no markup inherent to the file. The markup that you do see, so like all this color and stuff in the code, that comes from the RStudio interpreting the text inside the file and thinking about it in terms of what would this do in R? Like, is it a function? Is it an argument? Is it an object? And is it text? And coloring all those different concepts, different colors. Is it a comment? Coloring them, for me, green. Okay, but in the computer, it's actually stored as a pattern of zeros and ones. So that's voltages and not voltages, or actually I should say not voltages and voltages. So zeros and ones, with the ones being voltages. But those zeros and ones, called binary code, stand for a particular like encryption, which we actually call encoding, whenever it's encoding for some sort of I guess I think that's probably most of the time when it's encoding for different things, but I mostly see this term when it's encoding for text in some sort of format. So right now it's being stored in the Unicode transformation format, which you never see spelled out. You just see UTF or Unicode pretty much. Unicode is a really common tool. It's how we often are creating text files. And so many different programs could actually visualize this. And that's really why I'm mentioning this. It actually comes up later on because sometimes I will give data to you, but it is compressed. That means it's patterns of zeros and ones, which that's how it's always stored, but its encoding is as a compressed file, something like a zip file or a RAR file or a 7Z or a GZ file. There's all sorts of little types of compression that don't stand for text because text isn't a super efficient way to store data. These zip files are much more efficient, but they're harder to read. They require a separate program to decompress them. And then that restores the original text structure so that you can visualize it. If you ever get a file that just looks like gibberish, that's probably why, is that it was actually somehow stored in something that was not text, and that you needed to do some sort of transformation to it, probably unzipping, in order to visualize it. The alternative is that if you try to open like a program, most of the programs you get are not stored as text. They're stored as some sort of compiled code that has to have a separate program interpret them. Okay, well, that's it. So the extension just tells you how to open it. I have way too much text here. Let me just boil it down for you. The main thing is that it turns out you should probably always have the view file extension option enabled for your computer. So for example, if I open up my downloads file, it's a little hard to see. Nope, text didn't get bigger. Well, at the end of this file, it says .r. If I go here and I say view, show, file extensions, if I turn that off, it no longer says .r. And I could have put any sort of thing there. I could have made that a program that gives you a virus. Technically true. Kind of used to be a big problem. But with file extensions, I'm able to actually see the extension, and I know a little bit more about the file. That's the point of the extension, to tell us how that file should be used. I recommend always turning that on, regardless of if you're in my class or not, and here are 2 links on how to do that. Okay, keyboard shortcuts. I did this in all of the classes, but we're just going to quickly demonstrate it again. The real big important one is the ability to run code one line at a time. So there's a couple of different ways to do this. The easiest one is simply put your cursor on the code. So look, I'm just zooming back and forth. Zooming back and forth. These are just arrow keys doing this. But then if I press Control Enter, because I'm on a Windows system, it runs the code by sending it to R down here. This is how I want you testing your code. You're going to hear me say, now, I want you to use the hotkey. And you'll be like, okay. And then you use the hotkey. And like, man, that sure was satisfying. That's what you all tell me every time, 100%. Maybe not. Anyways, use it. It really does help. So it's either Control Enter or Command Enter. If you do, I do have a note here. If you do accidentally hold Shift while you do this, you'll run the entire file and it's very confusing, and you'll probably want to just clear your environment and start over from the beginning. Be careful to not press that Control Shift Enter. It's quite confusing. I do it sometimes on accident. I always mean to go turn off that feature. I don't like Control Shift Enter. I never do. It's just it's under the hotkeys. I could do it. Anyways, moving forward. The next one is you can hold Control to go faster. Got to go fast. So look how fast I can go back between hippopotamastroquedipololiophobia. I don't know. I'm sorry. I did this a long time ago. Is it like a fear of big stuff or hippos, perhaps? I don't remember. I should remember. Anyways, Control, really useful because sometimes you just want to be able to quickly go through word by word. On the other hand, you can use Home and End. Or if you're on a Mac, you can use Command to do this. So I'm using home and end. If you're using the command, you just press command, and then as if you were using control, you use the arrow keys to go all the way to the end or beginning of the line. Again, quite useful, especially for really long lines of code. One thing to point out here is that when I first sent this out, I had some of the Mac hotkeys just incorrect. I'm sorry, I don't own a Mac. But I've updated them, so I hope these help. They're quite useful. So command also does this on a Mac. You might want to add that, and then control opt, not control/command, which is I believe what it originally said. Next up, this is the big one. We're going to put it all together, and we're going to show you that you can very quickly run code in like a really like fine, detailed way, especially useful when you're trying to parse out what's going on with some in-between step in a piece of code. Like for example, what if I want to run just this? Easy enough for me, but let me run you through what I just did with my hands. So I have my cursor, right here. I'm going to hold shift and I'm going to hold control. Actually, what I did was I got fancy with it. I didn't even notice. I held shift and then I pressed end and then I pressed back arrow key. Very efficient, but it's because I've been doing this for so long. It's like playing a musical instrument at this point for me. It just all kind of comes automatically. Now, if I was you, I probably would have just pressed shift and then right arrow key till I got to the end. On the other hand, you might have also held shift and then either control or option if you're on a Mac. I said option, yeah. And then that would go word by word. But yeah, I guess technically the fewest keys are shift, end, left. Anyways. Shift, really useful. And you're often going to find that it's actually quite challenging to not do stuff like this. And then you run this and you get like some weird error message. And it's because right here, you managed to not copy a quotation mark. Happens all the time. And it's really why I recommend you avoid using your cursor or your mouse. Like really lean into these hotkeys. Practice them, learn to love them. They make your life better. The next thing is you're going to see that I'm constantly saving. In fact, I used to hold up my keyboard at this point in class because I had worn away the surface of my control key. You could see through it because it was transparent underneath the paint, and you could see through it into the internal section of my keyboard, which was nice, but I just got a new laptop this year, so I can't do that anymore. But Control S is going to allow you to save your changes. So first of all, I need to have a change to save. My file is currently black. That means I don't have any changes to save. But if I add a line break, that change has caused my file name to become red. And so the question of, do I need to save? Well, is the file name red? If so, then yes. And let me press Control S. Boom. No longer needs to save because it's turned black. Now I'm going to undo what I just did using Control Z. And then I'm going to save it. Now, why did it zoom to the end of the file when I pressed that? I honestly don't know. That was weird. Okay. That was weird. Oh, I guess when it saved it saved to the bottom. I don't know. That was weird. Okay, so I pressed Control Z twice. That put this back to where it was. So I undid twice, and then I pressed Control Z to save. All right, last of my new hotkey section. This is Tab. Tab is the best. Tab is great. It helps you avoid typing, which when you are as bad at typing as I am, is tremendously valuable. Additionally, it helps you pull up things like documentation and helps remind you of what you're trying to do. Really, you learn to love it. Like you'll see me just constantly flicking my pinky out to press the Tab button as I'm coding, just all the time. So the actual trick here was just for you to go through and put your cursor to the right of each of these things. But I'm going to show you from the very beginning. So let's say I am wanting to write a matrix function, and I start to type in ma right there. And then I press Tab. I'm like, ugh, it doesn't say matrix. I have to type more. Then I press T. Ugh, it still doesn't say matrix. But then I say MATR, and finally it just says matrix. And I'm like, thank goodness I don't have to type in IX. So then I press Tab, and it completes it for me. Ooh. Now, if I am trying to figure out, all right, I don't remember. What's all the stuff that matrix function can do? Oh, right. I press tab. And when I do that, this little pop-up menu appears, and it's got the different arguments that allow me to set the properties of the matrix function that let me create different structures and types of matrices. And that reminds me that the first argument in matrix is the data argument. So if I press tab again, in fact, you can even see it says an optional data vector, and then a bunch of stuff that's probably hard for you to interpret right now. So we'll kind of come back to that in a later point. But I press tab and I say, all right, well, some data is like 1 through 8. And then I say comma, because that's how we go between different arguments. And then I'm going to press tab again. And I press tab again, and now it's my options yet again. What are the remaining arguments that have not been set yet? Well, I have in row, I have in column. In row is how many rows. That's pretty easy to understand. If I say 2 rows, and then let's say I don't want to specify the columns. I want to be able to like change the data so that way it could be bigger or smaller. And if I said the number of columns, then, if I say the number of columns and the number of rows, that means only a certain length of data can fit. If I want this to be more flexible, I won't specify the number of columns. But let's say I do want it to first go, oh, I did that too fast. I get ahead of myself sometimes. What if I do want it to just go all the way down the row before skipping into the next column, as opposed to its default behavior of going down each column and then going to the next column? So if I do that, I can activate this by row argument. The default is false, that it doesn't go by row by default. But that's what it says in the tooltip there. If I come to by row, I press tab again, and this time I say true, it's now going to create a matrix by row. And then at the end of each function, we always have to close out our parentheses. And so I add in a matching parenthesis. If I'm not confident whether or not my parentheses match because this code got really big, I can actually put my cursor to the right of it, and we'll see that it like pulsates around. I don't know why I said pulsate like that. I'm so sorry. It pulsates around this highlighting on both sides of the parentheses. See, this is why you should watch the videos. It gets weird in here sometimes. I'm just talking to myself all day. We can now see that it added that data 1, 2, 3, 4 by the row, 5, 6, 7, 8, 2 total rows. That all worked beautifully, and I'm ready to move on with my code. If you already had code there and you're simply trying to figure out what each argument is, it turns out they go in order. This was the first one, data. This was the second one, by row. But this next one, the actual next argument was in column. It actually turns out that if I had just run this as is, I get a weird error message because it's trying to use true as in call. So it turns out you needed to say that this is actually by row. And we'll come back to this in the future, but that's the idea. So I wanted you to practice with your tab. You can either do what I did and try to create it from scratch, or you can just try to add in the names using just your hotkeys. No typing, just the hotkeys. Tab, tab, arrow, arrow, arrow. Shift, control, backspace, tab. Fun, right? Get used to it. All right, moving on. Syntax. Syntax is something that you will learn over time. The easy stuff to say is, anytime you have parentheses, there should be a match. Anytime you have a quotation marks, there should be a quotation mark. There should be a match. Arguments separated by commas. That's the big stuff. Really, that's a lot of it. Spaces almost never matter. They do occasionally, but just occasionally. One of those occasions is if there's a couple of symbols that we use that are comprised of multiple things. So I'm just going to say object 1. There's a symbol that looks like this. They have to go together. If you don't put them together like you do this, it means less than symbol and subtraction or negation. Together, they mean assignment. Ooh. There you go. So now I've created an object called object 1 that contains the string assignment misspelled and then the word ooh, which I don't know if that's actually a word. Anyways, that syntax, white space, largely ignored. So like all of this right here does not matter. All of this right here does not matter. All of this right here does not matter. This right here does matter. This is another example of where spacing does matter, and that's when it's been captured by quotation marks. This is actually storing a value, and that value is capital H-E-L-L-O space, 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 space. I lost track. W-O-R-L-D exclamation point, and that's what's stored. The quotation marks are not part of the string. They are simply how we tell R that we're creating a string. And just to better define string is a collection of letters and symbols stored within a single position of a character vector. More on that later. That's a lot of terminology, but that's the idea. So largely white space agnostic. The only spaces there that mattered were those ones between hello and world. Done. Line breaks often do have meaning. So as opposed to spaces and tabs, line breaks are often meaningful. However, they are still sometimes ignored. So for example, here I could add I can't just add random characters, but I could add a whole bunch of line breaks, and the only one that ends up mattering is that one between hello and world. And again, it's because it's been captured as part of the string. On the other hand, if I do print hi, and then I say space print hello, this doesn't work because different commands have to have a line break between them. If you don't have a line break between them, you can actually use a semicolon, which you'll very occasionally see me use, but this is equivalent to a line break between commands. So this doesn't work, but this does. And finally, this does as well. The difference being a line break does sometimes have meaning, primarily in order to separate separate commands. Additionally, one thing to point out is this error right here is actually fairly common, of accidentally usually putting multiple commands on the same line. And the frustrating thing is it's not an easy to understand error message. I don't know about you, but like, what? Unexpected symbol? Like, what does that have to do with having multiple consecutive commands? I know the background reason why that is, but like, it's convoluted and it's not really worth talking about. Just know, like, sometimes these error messages, they try to be helpful, but they're not always helpful. Cat is another function that's similar to print. One nice thing is it shows the line breaks actually as line breaks, as opposed to printing off with like this \n, which is a symbol that stands for a line break. So in fact, if I do hello and then a \n world cat, we'll print that out as hello line break world. And there's actually a little space right there that you can't see, which is always tricky because spacing's hard to look at since it's not visible. Just a heads up. Anyways, moving on. Now, please note there's no in this anymore because \n is what's known as an escape, and it changes the function of the next symbol. Again, more on that later. There's so much of that at this time of year, but just bear with me. That's the nature of the beast. Okay, moving forward into syntax. What is a function? How does it function? Functions are basically collections of code. So like objects store data and values. A function is an object. It's just an object that instead of storing like regular old values in something simple, it stores code. There are ways of putting options into it. So inputs, and it will process the data and it will provide outputs. Sometimes it doesn't actually provide any output. The vast majority of the time, though, R is written in that way. You give something an input. It doesn't change anything about the data that you input into it, but it then produces an output that you can use as you wish. I love this. I find it very like just like intellectually like graspable. I do inputs. It doesn't change those. And then what I choose to do with the outputs lets me control what happens next. Now, some functions don't quite operate that way. Some have their own like little special interpretations. Like a plot function doesn't really give you stuff in the normal way. Instead, it sends information to like a graphics program existing inside of our that's produced by R and then visualized by RStudio. Cat, similarly, it doesn't really give you information to use. It simply prints off messages into your console. So the thing to know about functions, though, is that we can change how they work using the different arguments. So cat, if I put my cursor at the beginning of the cat function, so that's after the open parentheses, I press tab and I get my little pop-up. I can see that there's a number of different options, but one of those options is ... which is interesting, right? ... basically means that it accepts multiple arguments that are not specified what they need to be. If I press F1, it allows me to open up the help file, and I can scroll through here. The help files are sometimes helpful. I will say right here, ... being our objects. Okay, I guess helpful. Maybe not the most helpful. The other arguments are actually quite helpful, like you can cat from a file if you use the file argument. You can choose what to separate each value with, which I actually have done right here. So this is a character vector. This is called a character vector, more on that later, which is what's going to be appended after each element. And so each of these will be a different element, and it's going to put this character after them. Not too bad, I think. If I come down to the details, which is where it told me to look for more information about the ... it talks about it converts its arguments to character vectors, concatenates them, that means sticks them together, into a single character vector, appending the given set argument to each element and then outputting them. Okay, so if I try that, I expect that it's going to add a dash to this because that's what my sep was. And then it's going to stick it next to this, also with a dash after it. And it's going to stick it next to this, also with a dash after it. And then interestingly enough, you're going to see that it doesn't add a dash to the end because it's only between them, actually. It's not always at the end. It's simply between each element, which actually, if you notice, technically violates how this summary is written. But remember, these are written by humans, and humans are wrong sometimes. And there we go. Cat is like print, but it formats things differently. Neat. The main things, though, is that each of these little values, separated by quotation or captured by quotation marks, being a single value, that's a length one character vector. More on that later. So sick of that, hearing that phrase, I'm sure. Second argument is. Third argument, like. I'm going to use my cursor. Fourth argument, print, but it formats things differently. Exclamation point, all one big string. And fifth argument, named sep. The argument will be named sep. It is then set equal to the value dash. These didn't have names because they didn't require them. The last one required a name so that I could tell, hey, this isn't just, tell cat, this isn't just one of those ... arguments. Instead, this is a value meant to change how you separate things. If I remove it, so I'm going to remove that argument, it's actually going to use the default value, which is a space indicated right here. So cat is like print. It just separated them by spaces, but it formats things differently. If I wanted to change this to something crazy, I could be like flubbity. Cat flubbity is flubbity like flubbity. That was weird. I don't know. Been doing this for too long. Let's keep going. Cool. Next up. How many arguments in the matrix function only? Think for a second. Pause the video. You got this. Matrix function only. Are you ready? Are you sure? Okay, I'm about to reveal it. Boom. Answer 2. Here they are. 1. An argument named data. That's going to change what data is stored inside the matrix. The value to that is the results of this C function. So even though there's a bunch of commas, these commas belong to the C function. Now I'll note, see how mine has these little like pink or purple, fuchsia perhaps, parentheses. That's because I use the rainbow parentheses option, which you can find the setting for in my slide set. And that clearly shows that this is like a nested function. So all of this is one argument for matrix. For the C function, it's 1, 2, 3, 4, 5. This is all one argument. 5 arguments for the C function. The colon, technically a function, has 2 arguments, 1 on each side, but it's got an atypical syntax. More on that later. The second argument for matrix is this in row, where I simply say in row is equal to 4. Finally, I could have left off these names, and the reason why is due to how R assigns arguments that aren't given names. They're assigned based on order. Well, the first argument is data. The second argument is in row. And so had I left off those names, I would still, in fact, have 2 arguments currently present, 1 and 2, and it would, in fact, still work the same way. The problem is if you ever need to go out of order, like if I wanted this to be the number of columns, I would actually have to specify that one. This one would not have worked if I didn't specify, because it's not in the expected order of in row second and then in call third. Because right now, in call is the second argument. It's getting a little high level, but that's how it works. It's a little bit tricky, but once you get a hang of it, it's pretty smooth. Yeah. Next up, what happens when something goes wrong? My friends, this happens all the time. So let's just give a quick introduction. Let's say we're a few weeks from now and we're starting to do some advanced stuff. There's like nested functions. There's these complex things called if statements that if this returns true, it does the code in between these curly brackets. However, the problem, one sec, pausing. However, the problem is that right now, I don't have this in curly brace. I need it. Well, when you have this situation, which is actually fairly common, you get stuck. And you see it, and this is more, I just need you to see this bottom left of the screen. When syntax goes wrong, sometimes you get stuck in the code. And you start saying things, and you're like, ugh, why can't I do anything? 2 + 2. And it's like, what? Nothing's happening. Hello? And maybe you can eventually get it to, no, I can't see it. Yeah, so this is the problem. It was like you're trying to do all this stuff and nothing's happening. Really what it's waiting for is for you to say this in curly bracket. More on this when we get to if statements. Once I added it, it figures out that it's the end. But the problem is how do I escape that? Now the answer is the escape button. So if you ever get stuck in this plus mode, which is very confusing, you simply press the escape button. Boom. Escaped. That's it. Remember that in the future. It's going to come up. Hopefully I headed off some problems in the future. All right. Next up, we've got the matrix function. The matrix function here, I am trying to show how I can align text. And this is just simply me demonstrating that because R is space agnostic for the most part, it allows me to do things like get creative in how I organize my code. And I can even align these values into a matrix-like structure in order to figure out how it will end up making it when I make the function. Now, it doesn't make it because I put them in that structure. Note, because it adds the data by column, it's kind of inverted from what I described, but it does let me line everything up in order to understand it really well. Now, if I did want it to do that way, I could actually have said by row as a new argument, and now it will actually go about how I expect. And if I wanted it to be perfect, I could say that the number of columns is 4 instead of the number of rows. And now it matches my matrix perfectly. Now what's happening here is I am doing something known as an assignment. I am using this symbol, which will take the output of the code to the right, which starts here. And because the end parentheses is down here, we'll run all of that at once. And it will store, note the direction of the arrow, that data inside of the object named mat1. So this is like saying X equals something. Matt equals this. In fact, if I changed this to an equal symbol, it would have worked. Although for a variety of reasons, I personally prefer to use this symbol. One thing that's mentioned here is that this is not the same thing. This is one of those rare cases where the spacing really matters. These symbols have to be next to each other in order to work the way it's working. Last thing, I can have RStudio do its darndest to try and figure out how to piece all of this together by holding on a Windows computer Control-Shift and A. And it will try its best to align the data. Now you'll see right now, it kind of moved everything over to the right. That's mostly because of this escaped code right here. So I'm going to take that out. But if I had wanted to, I could have then pressed Shift-Tab and it would reduce the indentation. So this is Tab, Shift-Tab, Tab, Shift-Tab, Shift-Tab. And now it's all nicely formatted. Now, before I forget, I'm going to undo that real quick. So I pressed tab so many times. All right, cool. Just making sure I don't accidentally overwrite my stuff. Because, like I said, I'm constantly pressing save. Okay, moving on. We were just past here. Cool. So many different symbols have special meaning. One thing that you have to be wary of is backslashes. Backslashes are complicated because they change the interpretation of the next character. So what this is currently saying is something special about capital H and then hello world, like just no H. Just sounds like I was trying to do a bad British accent, actually. But if I try to run this, it says, I can't do that. \H doesn't mean anything. Some characters do have special meanings, though. So \n stands for line break. And you can't see it when printing, but if this was a cat function, it would actually produce a line break and then say, hello, world. All right. That is this concept of escape. I'm more just trying to point out that while spacing is often benign and line breaks are sometimes benign, but take advantage of them. They're useful. Backslashes and many of your special characters are absolutely dangerous and they can mess things up. You can't just leave symbols lying around. Some other dangerous symbols are a angled quotation mark. So note this symbol versus this symbol. Look on your own screen if this is not clear on what you're viewing. Or a apostrophe versus a back apostrophe. They are not the same things and they can't be used to create strings. So this is most commonly occurring when you're copying and pasting from things like Word, which will automatically convert quotation marks. So the normal quotation marks we can type into angled quotation marks that are, I guess, somewhat more readable, but cause problems inside of coding languages. This is actually a fairly common problem. Yeah, but these quotation marks are super useful. The apostrophes are synonymous with them. It can allow us to do some fancy stuff. So let me just give you some examples. Here I am printing hello world, and you should be able to follow along with this pretty easily. I'm just going to press Control Enter and run it. And then I'm going to press Control Enter again, and it's going to run this next line of code. And you're going to be like, Nolan, there's no print function. What will it do? Well, R has to make a decision. You've just told it, hello world. You've given it a single value. You haven't told it to do anything with that value, and it has to make a decision. Does it want me to, does Nolan want me to store this as an object? Does Nolan want me to greet the world? What does it want me to do? And what R typically chooses to do with just kind of like loose data that's just been given to it, but you haven't told it what to do, is it print it. So it looks identical to the print function. So in fact, you'll often see that I don't say print. I just use the mean function, or I just say the name of an object, because what R typically does in that situation is it prints the data. Now, for more complicated data that doesn't really benefit from printing, it will do different things. And this is where it gets tricky. It's because of a property called class, and we'll talk about that soon. Anyways. Similar to quotation marks, we have the apostrophe. Note that's different from the backtick, which is located under your tilde. The apostrophe is typically located next to your quotation mark. Anyways, the apostrophe is synonymous with quotation marks in R. So if I press this, it just operates the same way. Please note, in the printed version, the printing shows quotation marks, not apostrophes. But this is kind of nice because sometimes we can nest them in case I actually want to use an apostrophe or if I actually want to use a quotation mark. So there we go. You'll note that when it prints a quotation mark, because it wants to show like this is a quotation mark and it's not the end of the string, it puts a backslash before them. If you didn't want that behavior, you wanted it to just print it like kind of raw, you actually wouldn't print it, you would cat it. Again, a different function. So you'll note that that's kind of the more raw version of that printed text. Whereas this is more of a symbolic version of the text that I've stored in there with these symbols added in order to define like, hey, this isn't just a quotation. This isn't the end of the string. This is actually a quotation mark. So escapes are commonly used in these sorts of situations. So angled marks are just tricky to use. So just, again, be careful. The angled marks are not the same thing. They just will cause problems. Avoid them. So I've mentioned escapes a few times now. Escapes are really handy whenever you're wanting to use symbols in a different way than they're normally used. So here's a quotation mark. If I wanted to include a quotation mark inside of a pair of quotation marks inside of a string, I would actually have to escape that quotation mark so it changes its meaning. Well, it turns out the changed meaning of a quotation mark in R means it no longer is the start or end of a string. Instead, it's just quotation mark. That's it. Just a plain old quotation mark. And that's why this doesn't end the string. This is all one big string ending here. Okay. Printing shows escapes, but cat does not. We've already demonstrated that. There it is again. We can use this feature to allow us to introduce line breaks. We can even backslashes. So here I wanted to show the end, so I had to backslash my backslash, so that way it would change how that backslash is being interpreted. Convoluted, right? Here's a slightly more simple example. I can even escape an escape to change how the escape is interpreted. So whereas this would have escaped my quotation mark, because there is an escape before it, it changes its behavior to just a backslash. It's no longer escape, it's now a backslash. And so it prints off a backslash. Well, it cats a backslash. Weird, right? Escapes are mostly, I teach them just because you will sometimes come across them and they're just very confusing if you haven't at least heard what's going on. Do I need to be able to type this line of code? Not really. In fact, I'm sure when I wrote this, I don't remember anymore. I'm sure I stumbled through it a few times and I started adding backslashes randomly until we got it to work. Not randomly, but hopefully you get the idea. It's a lot of this coding process is very experimentally driven. All right, we're done with syntax. Woo-woo. Now it's time to talk a little bit about objects and what they mean. So we're mostly going to be doing this next week when we talk about how objects are stored, what they mean in terms of like memory on the computer and class and type and all these different properties that they might have. But for the most part, what you need to know is that they are like variables in mathematics. They are ways of storing data. When we talk about structure, it's because unlike variables in mathematics, they can be quite complicated. They can be not just the value 1, it can be a matrix of 1 million values with 300 columns and however many rows that it equates to. I don't think it equates to the right number of rows if I did that math right. But anyways, that's the idea of an object. They're data, but they're often structured data. They're complicated. They have properties, things like that. That's the definition of object. They can also be very complicated. They can be things like a plot, which, what does that mean? Well, it turns out to be really complicated and often requires multiple levels of interpretation. But again, that's where we come back next week. To create an object is quite easy. We use the assignment symbol. We've already seen that symbol in this video, but there it is again. This is my preferred symbol. I generally want y'all using this. Mostly because it changes, it's a little bit easier to see when you have a mixture of argument assignments, which use the equal symbol, but an equivalence symbol is the equal symbol. I usually want y'all using this though. We can print an object by simply calling print, but first we have to create that object. You'll know if you've created it or not because you'll see the object in your environment. So right now I don't, but if I run that, now I do. If I print it, I'm just pressing Command or Control Enter. It prints it, but it turns out the vast majority of the time you're going to see me just print off the name of the object, but using just the name of the object. And that's because the default behavior for most of your simple object types in R is to print it. And so it's simpler just to say an object versus print an object. Okay, objects in R by default are mutable. That means they can change. And we use this quite often in this class. So I'll do things like analyze an object, use that analysis to extract from that same object, and then overwrite the original object. So I could even do things like take an object, to take its original value, add 2, and then replace it. If I did that again, it's now bigger. I could keep doing this in a recursive process that just keeps overwriting the previous value and makes it bigger and bigger. Neat, right? But they are mutable by default. They can even change type in class, which is something that I think is maybe hamstrings R in some more professional settings. But it's really nice for you guys because you don't have to really know all the details. It will do most of the things you tell it to do. You might be wrong and it might not be the best choice, but you know, you can. Though not tough. All right. You can use equal symbol. I just don't recommend it. Most of our community uses the kind of arrow looking symbol. And so that's what you'll see me use. Next up, functions. Functions, like I said before, are objects that instead of storing just regular old data, they store code. They store a process. And there's a lot of built-in functions. We'll even be getting up to the point where we're making our own functions by combining other functions. It's pretty fun, actually. Custom functions is one of my favorite units. One of the harder units, too, because you just have to start thinking in a weird way. So learn it now really well, and it makes it much, much easier downstream. All right, let's go through it. Here I'm going to create a dot object. It's going to store the value A. If I wanted to print that out, there it is. It's storing the what's called a character value, A. It is length 1. That means it's got a single value. One thing to know about R is that most of our simple types of data are actually vectors. That means they have multiple positions possible, as opposed to just a single value only. So yes, this has a single value, but it actually could store many different values in separate positions. We're going to demonstrate that behavior. So here is a dot object. So it stands for whatever is in here. Note, that's different from me saying a dot object, which is the string a period object. Without quotation marks, it's the object a dot object. Now, the argument and function that I'm currently using is the C function. The C function combines each of the arguments that you give it into a single object. Well, the first argument is this letter A. Note how I said that. Rewind a few seconds if that didn't make sense to you. Then the letter B, then the letter C, and then a single string containing HELLONOLAN with a space in there. Note, that is going to result in 4 different positions. Letter A, B, C, and then this is going to be our 4th position. And this kind of just harkens back to a strange concept for a lot of newer people in this field, is this difference between position within a value and the positions within what's known as a vector. This is a vector. It is a collection of data that has a single dimension. That single dimension being position. So position 1, position 2, position 3, position 4, across position 4, across a single dimension. A vector. Cool. New definition. We're going to get real deep into that next week. There is a difference between character vectors as well as number vectors. You'll note how they print off differently. But again, here, if I am counting the number of arguments, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. But each of those arguments are set off by commas. The resulting object, because each of those values was length 1, is 12. If any of those instead were much longer objects, so this is a really big object, it would result in a much bigger version of an object. So now we have a whole bunch of numbers. But that's the job of combine. And this idea of being able to like add arguments and take away arguments and experiment with it, this is something really that I need y'all to learn. Please note that for each of these examples, though, I have been assigning the output to an object called an object. In order to visualize what was going on, I had to then print it off. However, if I do not assign it to anything, the default behavior for what I'm going to be henceforth referring to as loose data is going to be to print it, at least the majority of the time. For some of the more complicated objects, it doesn't do this, but for most of simple objects, it simply prints it if you do not assign it to something. Assignment is, however, technically just a function. It's a type of function known as an operator, which is defined right here. It's basically a function with atypical syntax, like it might just be a symbol. But it is technically a function. In this function, you have two arguments. You have the thing to the left of the symbol, and you have the thing to the right of the symbol. This is a very typical syntax for R, is that like plus actually just takes everything from the left. So 3 plus 4, it's a function that takes the first argument, the thing to the left, and adds it to the thing to the right. And when I run it, I get 7. Here, I'm demonstrating a way of using these backtick symbols. That's the symbol underneath your tilde, typically on a keyboard. It's going to take an object name as its first argument, and it's going to take the value to store inside of it as its right argument. And so this was equivalent to me having said left object, right data. Neat, right? Nobody does this right here. This is a very strange way. I've probably done that on purpose a handful of times in my career. Usually when I needed to like make an object that's name was possibly changed. It's like depending on certain contexts. Very rarely though is anybody doing this. Operators are typically simply used as you would in like mathematics or something like that. So here the plus symbol is an operator that takes things to the left and adds them to the right. The colon symbol is an operator that takes the value to the left and creates a vector going by 1 to the value to the right. So here it's going to go 1 through 100. Because that's in parentheses, that's going to happen first, and then it's going to add those values to 10,000. So then I get 10,000 plus the values 1 through 100. Make sense? Cool. Operators, technically just functions with an atypical syntax. Many operators are actually simplified versions of more complicated functions. So for example, the colon symbol is actually just a shorthand for this longer piece of code. Go create a sequence is what this stands for. From the value 1 to the value 100 and change it by the value 1 each time. So that just produces the same thing. Obviously colon, a lot easier to type, huh? So next up, we have a concept called recycling an element-wise operation. Now this process is quite handy. It is a process that allows us to repeat values and repeat a process over and over based on one of the arguments being longer than the other arguments. It's most commonly encountered whenever you are doing things like mathematics, but it's present all over R. The concept of element-wise is present whenever you're taking something that has multiple positions and you're repeating a process position by position in some sort of typically symmetrical way. So let's give some examples. It's much easier to show than to say. So here, if I break this apart, I'm going to start with a matrix. Here's a matrix that's got a bunch of zeros inside of it. Here is a vector. It's the values 1 through 8. And I have told R, hey, combine these. And it's going to do what's known as position-wise, element-wise operation, and it is going to try to add those together. And if you guess right, you're going to determine that it's going to go down across each column and then start on the next column and add to that. You should hopefully be able to see how that's working right now. Now, the reason why it went down the column first is because that's just typically how R works on matrices. It's just kind of a quirk on R. It's present throughout R. It typically, by default, starts off by filling rows or columns first, then moving on to the next columns. There are ways to get around that, but for the most part, that's the behavior, and you just kind of have to, it's easiest just to work around that, that central concept. Finally, I then have a big set of parentheses causing 2 to the power of whatever was inside of that matrix. Now you have to ask yourself, do you think it's going to remain a matrix, or is it going to somehow get converted into a line? The answer turns out it's going to stay as a matrix. But if you think about it, like that's actually kind of a complicated process, and it requires you to make a bunch of assumptions you really couldn't have known. This is really just where practice comes in. Like, no one's memorized every single rule, and I've been doing this for 10 years. Was I 100% confident that that's how that would work out? Not really. And I wrote this script. I was pretty sure that's how it was going to work out, but I wasn't 100% sure. But you know what? It was really easy to find out. I tested it, and yeah, that is how it works. And now I can move on with my life. You're going to hear me say stuff like that a lot. Testing it and simply trying and figuring out how these things work is the way that you learn to code. Like, it's just that kind of interactive process. So let's try a few more. Here we're going to see an example of recycling and then element-wise or addition. So if I look on this right side, it's really long. If I look on this left side, it's really short. That means it's going to have to recycle that 1,000 in order to add it element-wise to each position in 1 through 10. If this left side is the same length as the right side, however, there is no recycling, but it does still do element-wise addition. So when I run all that together, this gets added to this, each position. Now, doing a non-element-wise addition is going to result in something completely differently. So here is that same code, repeat 1,100 times. Or sorry, let me change that to 10. So repeat, let me clear my console. Repeat that 10 times. Create a vector 1 through 10, and then sum them all. That's a completely different setup than that. And so you get a completely different value. But this is technically true. That sum does not add it up element-wise. It just adds up all of the positions in totality, not position by position. But don't worry so much about this. It becomes very intuitive. Oh, and there was another typo there. Dang it. I've been changing stuff over the years. Yeah, there we go. But that's the idea, is that non-element-wise addition, a completely different process. And it becomes intuitive over time, to the point where, as you could tell, you just don't even have to think about it anymore as you do it. But you have to practice to get to that point. Note to self, go fix that. Next up, we got the dangers of recycling. So this isn't super common, but I have literally rejected a paper over it, so I always have to mention it. Recycling can be dangerous because it happens silently. Most of the time, if you have something that's like one value added to a bunch of values, there's no question. But whenever you have something that you expect to be the same length, if you're wrong, weird stuff starts to happen. So here I have 1 through 3, and I'm going to try to add 1 through 7, and it actually attempts to do it. So it's going to take 1, and it's going to add it here. Let me actually do this one more time. 1 through 3, 1 through 7, and then all together. So it's taking this number, adding it to this number, element-wise, to get 2, 2 to 2, 4, 3 to 3, 6, 4 to 1. So it starts over when it runs out. So that's it recycling that initial shorter vector. To create 5, 5 to 2, 7, 6 to 3, 9, and then 7 to 1, 8. But it gives us a warning message saying that, hey, they're not actually multiples of each other. Are you sure you wanted it to do that? Because that's kind of weird, right? Like it's just doing 7 to 1 and then leaving these extra 2 3s hanging out there. Thankfully, it gives us a warning message, which is actually lovely. But if they were not the same length, but they are multiples of each other, it just silently does it. So here, 1 to 3 plus 1 to 6, that adds up, or without any kind of remainder left over. And so there is no warning. And this isn't usually a problem when it's very small, because you can see the problem as you visualize and check your code. The problem comes in whenever you encounter a huge data set. So let's say in your homework coming up, you have 250,000 rows, and 50,000 of those have a unique meaning. Groups of 50,000 rows have different meanings because they come from different sequences. But since 50,000 is a multiple of 250,000, there's a chance that if you were just working with those numbers, you might accidentally like combine them in some sort of weird recycling way that just gets really confusing. And you might not notice because as long as they're multiples of each other, there's no warning message produced. And I've seen that many times. And that's where I was saying, like, I rejected a paper because they did an analysis, but it was just wrong. I don't even remember how I discovered it. It was like a real subtle problem, but I think I just noticed a pattern. I was like, that's a weird pattern. And then I went and looked at it, and yeah, they just messed up the math because of this recycling process. So just be aware of it. So this recycling is an example of implicit changes. This is where like R is it has to make changes to the data. Like it has to repeat that shorter vector. And it does so without you telling it necessarily that, hey, first of all, I need you to repeat this twice in order to make it the same length as this. This is an implicit change. There are ways to explicitly say things. So for example, here, I was explicitly saying, repeat this 100 times, and then add it to this length 100. So there was no implicit coercion in that case because it was all explicitly done. And that's a major difference, implicit versus explicit. Explicit is when I say something, implicit is when R does it without any sort of permission or me necessarily saying do this first. R does a lot of implicit, and it's not super like explanatory of this. It's something to watch out for. But we're going to talk more about that later on. Okay, so this next step is just having you create an object called myLetters, and it should contain the letters of your name. I want you to use the combine function to do so. And you should pause the video right now and try to do that. To give you an example, though, the function, if I was doing it with my name, the length should return NOLAN, so length 5. All right, try to do that. Pause it. You ready? Ooh. All right, I'm going to press it. All right, there it is. So if I wanted to do that, I would just type in this right here. This would be the answer. And then this is a second line of code proving that I was correct. Now note, this is 5. Yes, I know how many letters are in my name. 5 different arguments to the C function, which then combines them into a single vector. That vector looks like this. Each letter separated into different positions within a character. Note, it's not NOLAN. It's in, and then a different position, O-L, A, and in. That's what C does. If I actually wanted it to stick them all together, I would actually need to use a function called paste, paste 0 specifically. And in that case, and I would need to say collapse them. And in that case, it would actually stick them all together. But that's not what I was asking you to do. I was just showing you why it doesn't do that. So separate positions versus all together. All right. Lost my flat. Moving back down. Next question. Make a script file named greetingscript.r stored in the location described below. I want that location to be here. Okay. Well, the nice thing is I can just easily make that. Make an R script file. Name it greetingscript.r. It's in the right location. I can prove this to myself by clicking my handy source on save function. And I can see that this is the code RStudio helps me generate in order to run this script file. And if I paste it, hey, that's still right. Now it wants me to add code that will print off the message hello greeting. However, it should do this by creating an object named greeting and assigning it the value hello world. The second line of code should then print the object greeting so that it just prints off a message. So I'm going to do that in a second. So you may want to pause here and go do that. Create an object called greeting, assign it the value hello world, and then have it print off that object. So I'm going to go do it now. So print, I forgot, greeting, hello world. Can't remember if W was capitalized. And then it's going to print greeting. And we should always just test our code. Okay, that looks pretty good so far. And then if it prints it, looks good. I'm going to save that file. When I save it, because I clicked source on save, every time I save it, it's going to try to run the whole script file. And indeed, right now, when I do that, it prints off hello world. Cool. The next things is it said, check your code by the following and or picture in slide set. So there's a picture with like showing what this looks like. But first, clear your environment. So I'm going to clear my environment. So there's nothing here. When I run this, it should do everything I just said. It should make an object called greeting, and then it should print that object's value. So I'm going to clear this as well, just so I feel like I'm starting from a clean slate. I ran it. There's that source function happening. It did print off the message hello world, and that's resulting from this object having been created. And that's because that's what source does. Source runs each of the lines of code in the file. Last section. The help files are where we can get help for the properties of different functions in R. This is incredibly useful, and you're going to see me do this constantly. The easiest way that I typically get to the help file is a single question mark and then the name of the function. So for example, if I wanted to see the help file for the mean function, I would simply do question mark mean. As I do that, it pops up this file. Now, there's also another way to do this, and that is described right here. So let's try it real quick. So after typing in the mean function and then the open parentheses, press tab to bring up an abbreviated help file. That's what we're seeing right here. Sometimes you will have to tell it the type of data you are working with in order to get details on how that function will work with the input data type. So like right now, it's saying X is my only argument that it knows how to interpret, and that's because I haven't told it what type of data I want to collect the mean of. That means that I need to at least tell it like I have some numbers, so I could say like 1 through 100. And then if I press comma and press tab again, now it's pulling me up the help file for numbers, which is, you can see right here, .default. This is like the default way of using mean. This is a complicated process, but it happens fairly commonly. It's called the S3 object methods. I don't really need you to go too deep into that. Just know that some of this is contextual, and sometimes you'll need to give it a little bit more information to get the right help file. But now that I have the right help file, I can look through these different options and I can make the right choice for my data. Another example that's a little bit more fun to use, I think, is the plot function. So I type in plot and then I press tab. at first, it requires me to say at least like an X and maybe even a Y. So let's try saying X, and we're going to say that X is 1 through 10. If I press comma to start the next argument and I press tab again, now that I've defined X as a number, it's telling me that, okay, well, I know I need to use the default plot type. So I could say like Y equals, I don't know, cosine of 1 through 10. It'll be fun. And I can say I want to do a line plot. And then I could say I want the x-axis to be logarithmic. It was kind of fun. I've never actually done that before. Then I'm going to say I want the main title to be blah. And through these efforts, I can start to create a plot. And then if I don't like things, I'm like, okay, no, a logarithmic scale didn't really make sense for this. Okay, that's looking better. I don't really love the type being a line plot though, so I'm just going to change this to some of the other types. Let me go look at those options again. So P for points, L for lines, B for points and lines. That's kind of cool. Let's do that. B. Love it. I didn't actually. B looks really good. I should be using B more often. I like that. And then I could start kind of riffing like, okay, I want more plots. So I'm going to say 1 through 100. And then I want more points. And then I'm going to divide that by 10. So that's going to put my points closer together. I'm going to do the same thing here so that they're the same length. 1 through 100, divide it by 10. So now it's going to be the same shape, but they're simply closer together. There's 100 or there's 10 times more points. If I wanted to, I could keep going with that. And now I don't even need those points anymore because I have such a smooth line. So then I can go back and be like, all right, I want to go back to the line plot now. And hey, that's a beautiful little cosine plot. And this process of like kind of using these help files to like just iteratively look up what are some of my different settings and exploring the documentation, that's actually like how I routinely use the help files. But to show you where all of this is coming from, and to be fair, I also often am looking at the help file directly. Let's actually break down that help file. So this is just describing that process of where you kind of need to go through that process. I've already shown that, so I'm going to move forward. Scroll back up to the hotkey section where I go through tab if you want to see that process. There's a little practice question where you can try to do this within about 16 keystrokes is about how far I got to go. Yeah, I did. I typed it all out for you. All right. The help file is this next section. So the help file can be confusing, especially when you don't know what you're looking at. The main thing to know is that there are different versions of different functions depending on the type of data that you're giving it. So like numbers will be worked on differently than times, and characters will be worked on differently than numbers and things like that. That's why that help file, or yeah, the tooltips changed as I gave it more information. So until I told it numbers, this is all the help I got. But once I gave it some numbers, then all of a sudden it's being more helpful. Mostly you just need to be aware of it. There is a good reading here. Let me just check to make sure that file is still working. It is. Still a nice little discussion there. That'll help explain it. Okay. Last part. What is the help file? The help file has a number of different sections. Let me just open that up. The usage section is probably the section I look at the most. The first one's often like the generic and isn't super useful. We're typically going to be using the default S3 methods until we get to more complicated packages in the bioconductor suite. So that's when you'll need to look at some of the more fancy help files. The arguments being set up are where I can see definitions for each of these different arguments. This is where it tells you what can be a value. So typically that's where students mess up, is they try to use a value. That's not the right structure for that position within the function. So let's break this down for this particular example. Here, X is the object that it is going to calculate the mean on. it also comes first. And because it comes first, that means that if I just say mean of 1 through 10, well, the object one, or the argument that 1 through 10 gets applied to is the argument x, because it came first. And this is super useful. That means that I don't actually always have to say x equals 1 through 10. I can just say mean of 1 through 10. Additionally, if I add further arguments, it's going to apply them in order. So if I say trim off the 20% of the distribution, which is how trim gets used, I have to give a little bit more data to show this. So let's have like some outliers. So there's a bunch of zeros. And then at the very end, there'll be like 100. So the mean should be much higher. But if I'm trimming off those extremes, the mean is still just 5. Whereas if I had left that in, those 100s really drag up that mean because they're outliers. So that's the trim argument. But the reason it got used this way is because it was the second argument. Now, if that seems confusing to you, it is. What I usually recommend is just always explicitly name your arguments, especially early on when you're learning, and you avoid any issues with this. Finally, na.rm is a logical value, so that means it's going to either be false, no exclamation point, all capital letters, false or true, indicating whether na values, stop raising my head up, whether na values should be stripped before computation proceeds. So let's just add in missing information, so not available information. By default, na.rm equals false, and we can see that in the help file. So by default, I'm getting missing information back. But if I add na.rm equals true, which is a logical value of true or false, it is going to strip out the na values before calculating the mean. And so now I get back to that mean I was getting before with my weird trim value. And that's how these arguments are interpreted. Now there's also some other sections here. There's things like more definitions of what happens when the trim is weird. So like the default value is that it doesn't just randomly remove data, which seems pretty logical, I think. And then this further defines how the trim is calculated, which is a little bit hard to understand, although I feel like they've improved it in recent years. I think it used to be a pretty bad description, if memory serves. But anyways, this is describing where this data came from, 1988, the year I was born. And then finally, we have some related objects. And then this is really the last portion I'm often actually looking at. The examples give you some great examples of how you could use this function. So this just helps with syntax, and like you can even copy and paste some of these examples typically and try running them. And then that gives you something to experiment with and make sure that you're using and understanding how it's working. Cool. So applying all of that to here, we can try and predict what is going to happen. So here I have an object. It's got some small numbers. It's got some big numbers in it. This small number is really small. This big number is pretty big, but not nearly as big as that negative value. And then we have a missing information. And so if I call mean, it's not going to work. I want you to fix that. So just take a second. Make sure that it just returns the actual mean. Okay, I'm about to do it. I'm going to add in a comma because I need to make a second argument. This is going to change how mean works. That means we need to modify its arguments. And then I'm going to press tab, and I'm going to press tab again after navigating to na.rm. Then I'm going to press capital T, and that stands for true. Or I could type in true fully. Either one will work. When I do that, it now removes the missing value. Here, this is asking you to think through that process I described on how arguments are assigned. Remember, they are assigned based on order, which if you correlate this with the help file means that this will be the X argument. This will be the trim argument, and this will become the na.rm argument. Now, this next one, I haven't actually given you enough information. We actually have to think through this process right here. So it says user named arguments are set first. Well, in this next example, this has been user named. So I've said specifically x equals an.object or an object, which means the rest of these will then be applied to the rest of the arguments. And this is what this second line says. It says remaining arguments are then distributed to non-user specified arguments based on order. So true is going to be currently applied to trim, and 0.1 is going to apply to na.rm. And that's a problem because, well, trim can't be the value 1, and na.rm needs to be a logical value. So if I wanted to fix this, and this says, produces an error, what is 0.1 in this example? If I wanted to fix this, I could just say that, hey, that value actually should be trim. And this value should be .na.rm. When I do that, now it actually works how I would expect. So this last question asked you to basically do something like that, but to calculate the standard deviation of an object. And so please try to do that. And I'm about to show you the answer. Okay. So if you didn't know, you would look up the help file for SD. There it is. We'll see that it looks a lot like the help file for mean. So I would just start with SD, the X object. I just press tab to open that up. Press tab again. And object. In fact, I can probably stop typing and then just use tab to help me finish that text. And then I can say na.rm equals false. End parentheses. Oop. I need it to remove the missing values, not keep it. So I'm going to set that to true. And there we are. There's our standard deviation. That was longer than I thought it was going to be. I was hoping for an hour and a half, hour and 36. I do hope that helped though. This is a long process and a long road, but you got this. So go through, scrub through what you need to review again. I will say the hardest things for students are these argument setting rules. So review through here, like really, internalize this because we're going to be playing with these concepts a lot. And they're commonly missed questions on the exam because students will play with it but never fully understand how they're working. You should fully understand how they're working. So go through this process of assigning objects and really think through the ramifications of what we set up here. You can even play with it. Try putting these in a different order and then making sure that they all work in the right way. But it's because the names are set first, then the non-set arguments are distributed based on the order, and you have to look up that order in the help file. And then the default values are only used if they're not set in the above steps. So like for trim, if I never specified trim, it remains 0. If I never specify na.rm, it becomes false. Those are its default values. More on that ad nauseum in the future, but I sure hope that helped. I'll catch you next week.